So you can move them down. All I did was give you a scene. He gave you a scene with 3 arms and 3 blocks, and it says, arrange the blocks so that your robot arm can touch all 3. Do not put the blocks in an arc. In other words, you can't just sweep across and go tick, tick, tick. That's not it. It's going to be, because you have, every one of those bases has a shoulder that rotates, which means you have to go further out on a few of them. Or you have to come inward. So you have to, that's the whole point of it, right? So, to that end, we have, you have to do that. Now, where you put the blocks is up to you. I don't care if it's like right next to each other or far apart. There's advantages to both. You can choose whichever way you want to do it. But right now they're just set at some height Z. They will fall to the ground. It doesn't matter if they fall to the ground, number 1. But number 2, you could just move them down to the ground. There's nothing to say you can't. You just can't move the blocks into an arc. Okay? Does that answer your question?
Andy?
No.
No, actually that was Wesley.
No. Well, I'm looking at something else related to this that I could explain it well.
Does that answer your question though, Wesley?
It's just when you start it, they just sink.
Yeah, they just land on the ground. They're in the air.
No.
All right, let me open it up and show you guys. I opened this up already talking to somebody else.
I haven't even started this. It's the for 4830. I haven't even started this.
Like it goes 36 lightning inside the room.
Oh my god, you gotta be kidding. First it takes like a bunch of units with the scenes. You gotta be kidding.
Like when I open the screw, I can't see it. But it just let me know. It's like any more script. I'm trying to figure out something. I literally installed it and just started looking at it. We're continuing Jacobians. Alright, so this is the simulation file that I posted for you guys. Right? So here they are. And when you press the play button, they drop. Yeah, that's okay. There they, and then there they are. You just need to touch them. You can put them wherever you want them.
See, with mine, it actually just disappears into the
What you might have done is change their behavior, some properties, so you make sure it's respondable and dynamic.
Oh.
You might have unclicked that for whatever reason. I don't know how. Because this is literally the file I posted.
Maybe when I moved it closer to the premise cell thing.
I don't know. Yeah, Andy, what?
For me, whenever I try to open the script, nothing appears, so I can't do anything to like make the script or anything.
That doesn't show up? Nope. It should.
But it doesn't.
On none of them.
No, at all.
Are you sure you don't have it open on another computer and the window is behind somewhere? I'll have to look at your setup. I guarantee you it'll work. It's not a user error. I've been using this tool for over 10 years, 15 years. I've never had that happen except for when it would show up over on another monitor and it was hiding. My MATLAB tends to do that too. So if you had it on another computer, and you had it on that second computer, and then you no longer had it on there, then you double click it, it's going to that other computer somewhere, or that other screen somewhere. That's usually what that problem is.
Well, I think I'm gonna have to redo it on my, because I did it on my desktop, now I'm gonna do it on my laptop now, see if I can.
I couldn't tell you, but generally that's the problem.
when you need like multiple monitors?
Yes.
Okay.
Yeah, sometimes if you open this on multiple monitors, and you had this on another monitor, you had the editor on another monitor, and there could be another problem that you might have set up. Here's another where it could be. Where is it at? You can tell it to use an external editor. You might have accidentally told that to happen.
I think I did tell it to use an external.
There you go. That could also be the problem. So try to open the external editor.
Okay, I think I'll look at that then.
I'm trying to remember where that's at. It is a setting, because I've used it. Like if you want to go to, not so much that, but like say you wanted to have it go to Notepad++. It could easily go to there, kind of thing.
Okay. Notepad++.
So you might have that set up in there as well. I'm trying to remember where you have that setting. It's kind of buried. Let's see.
That's cool.
Developer tools. I'm not sure where it's at. I know I've seen it because I had used it before. If anyone else happens to know where it's at, top of my head, I don't find it.
Was it not the external model? I think you were hovering over like tools or something. It said something about an external model.
No, yes,
Up one.
I went to tools and I don't.
Here it is. Maybe it's under. It's an external editor is what the checkbox would be.
Wouldn't it be in tools?
What?
Wouldn't it be in tools?
I don't know where it is. I just told you that. I don't remember. But it is somewhere in there. I don't use it very often, so it could be under settings. Yeah, I think it's because I remember it being more like a checkbox, like a tick box, like this. But this is simulation settings, so. At any rate, that's more. That could also be a problem. Other questions? How many are done? Not too bad. Just gotta work at it.
It was like literally changing one of the values for each.
Yeah, it's not that hard. Yeah, it's trial and error. But then you gotta still do the gauge parameters that go with it and then the forward kinematics that validates your design. That's all. Much like the problem on the exam, given the FK, right? How was the exam? Fair?
Yeah,
I think it's fair.
So for the first, because I know
Don't give me the answers away, John's got to cover it.
You'd like.
No, let's speak vaguely. Because you're gonna take it.
It's Wednesday during your office hours. If you guys, I can step outside for 5 minutes.
No, I basically it was everyone was under the impression that, because there were 3 parts. The first part we thought we were right, you said we were wrong, and then the other 2 parts I felt fine with.
Okay.
But obviously,
I didn't agree. You could be right. I don't remember. I didn't even touch the exams this weekend. I got so busy doing a million other things. Thursday was getting ready for a show and tell for elementary schools, K-8 with all the robots. Friday was that show and tell, and then dropping them back off here that night, talking to both NGCP and ABL guys. And then Saturday was family stuff in the morning. I had to do a ton of yard work Saturday afternoon and Sunday, and then here we are. So I didn't even touch them, to be honest with you. So the good news or the bad news? Do you guys want the exams before or after spring break?
After.
Okay.
I've been doing.
All right, done. That's that. I don't hear an answer, forever hold your peace. That makes it actually easier for John to take the exam, which is excused, so I will grade them all together. I should have them when we come back. I did start glancing through them, and it was good. Everything looked good so far. There were no surprises. I think, and you guys may be right on question one. When I did it, I thought I did it one way, but I'll double check my work. I just glanced at it. When I don't actually do the exam after I write the exam. I kind of like spot check it. So sometimes it works like, oh yeah, I didn't work out. Oh, who cares? Doesn't matter. It'll still be the right answer, no matter what. But yeah, it was really just performing the task. So we did a review, John. So I don't mind telling you this to study. You're gonna want to know, make sure you can talk to everybody about not what was on the exam to the point with the questions, but I told them.
Like the general thought.
Was there anything I told you that was not on the exam that I said was going to be? It was all very straightforward. For kinematics, John, no differences in IK. Quaternions, why they are, what they are and how they're different than rotation matrices. What is a valid transform due to a valid rotation matrix or submatrix, and how to operate on those transforms. Know the DH parameters from an arm. So this way I can give him the same questions because I'm not giving you guys answer the exams back. So, it means I don't have to read it and make an exam for you. You have an excuse. How do you guys do anyways?
Oh, it was awesome.
Yeah, did you guys do well?
Yes, we did.
How did you guys place?
Oh, no, so we weren't competing in this part. We
Oh, okay.
already competed.
Oh, got it, okay.
Only the top 4 colleges get to do the oral argument.
Oh, okay.
And it was amazing to watch those kids, man. They
You
were
learned a
getting
lot, huh?
shredded on stage by the industry experts, and those were the top 4 out of 33 teams.
Being shredded is all part of the rite of passage.
In front of 500 industry professionals.
So here's the thing is, and Maria will know this quite well, I will shred them on NGCP on purpose, so when they present in front of Northrop, they're not as bad. They will still get shredded, but not nearly as bad. It's good for you guys. It truly is, because that's where you grow. It's easy for us to all convince ourselves we're right and drink our own bathwater, but that's so. You guys over the expression, drinking your own bathwater?
You're the only person.
It's a generational thing. That's all I'm gonna say. It's like saying out of pocket is totally different for you guys than it is for us. Out of pocket means what?
Random.
See, no, it doesn't. It means you're not available. Huh?
So what?
What? I guarantee if you Google out of pocket, it will say unavailable.
What do you say?
Yes.
You were not available.
Out of pocket means you're unavailable.
I'm not gonna argue. You did this one Thursday. Remember it.
Out of pocket is slang for behavior that is inappropriate.
What else does
unreasonable?
what up for?
Unexpectedly wild. That's not
Urban Dictionary?
Availability, in availability terms, it means that you're not.
You're unavailable.
Yeah. But the first thing that pops up is like,
That's because it was written by your generation. Go look it up in a Webster's. Okay, anyway, makes sense? Okay. Anything else that we went over on Monday that I told you guys that I didn't tell John right now? I just want to have a fair shot at it.
Unless you want to tell me about the 5th question.
It's extra credit.
Oh, there's an extra credit question.
Yeah.
You still need to know it. But you have to also make sure you know how to do the transformation algebra or transform arithmetic.
We bring like validations.
Yeah, be sure to know if a matrix is a valid transform and why, and what you need to do for that. How do you show it's a valid transform? There's the 3 criteria. You only need to show 2 of the 3 criteria. And you all know that by now. I beat into you guys, and those 3 are what?
orthonormality.
Okay, orthonormality. Determination equals 1.
Unit vector units.
That's the orthogonal. The other one is or the inverse equals transform.
Yeah.
All right. Anything else before we go in? Okay. Simulation. Any other questions on the simulations? It is due tonight at midnight, so you could ask questions today.
I'll show you.
Can you show me what yours right now?
Yeah.
Oh.
I don't know if it's right.
Well,
Later,
now.
after.
Briefly, I have to go to class right afterwards, depending on how long I'll take.
It's just a minute.
Possibly.
Mhm.
I don't know.
Okay.
We'll see. Okay, other than that, are there any questions? So again, going back to it, you may use any 3 arms you choose. You may use any of the 3 arms, and you're showing video of it doing it, and you're providing the code that you have right here for it to move.
Actually, I do have a question.
Yeah.
For the robotics arm, that second joint, is that considered an offset? Because it's like a weird, like upwards offset.
From here to here?
Yeah.
Yeah, you could consider there's a slight offset. There's actually,
Yeah, you go from that one to the middle one.
you're talking about this joint right here?
Yeah,
Yeah. Technically, there is an offset, but it's not a Z offset.
it's not, it's like a Y, right?
Yeah, it's actually a Y offset. So if you want to ignore the Y offset, you don't have to worry about it.
Oh, okay.
I'm not gonna kill you on that one.
Okay.
Yeah. It's just a physical, limitation. I don't know which one's easier. Yeah.
If we include the scene file, do we still need to separately include the script files?
Yes, script, video, and, the scene. Yeah. And then I also ask for a PowerPoint or write-up, yeah, and the PowerPoint write-up. So you could take a picture of it and draw up on it or mark it up as you want to. So yeah, and so zip all that together and you put that in the submission.
We want it zipped and not separate files?
It doesn't matter. Zip is easier because I download it into everyone's directory and that's how I keep track of everything. So it'll download everything into a zip and then all of your guys' zips, when I unzip that one, have its own zip. And that's why I asked for the format I did. So it's last name with the files. So that way it already alphabetizes you guys. By the way, I do have pretty much everything graded, but I'm redoing Canvas, so it'll show the different allocations. That was supposed to be on my to-do list this weekend, so bear with me on that. But everyone's other stuff you have submitted looks good, so no worries on that. Remember, the homeworks were graded for attempt, not for correctness. Always been that way. But I did look at the homeworks, everything looks good. So you guys are doing well on all that stuff. And the other simulation you guys put out there looked good too, so that was a homework simulation. This is the legit simulation. We'll do one more legit simulation. The 2 simulations that'll count for 1 exam. So it's like another way of doing an exam without doing an exam in class. But I think I like doing it this way better because I think you learn more, in all honesty. Before we move on, any other last minute questions on sim, on homework, on anything else we've got going on? Wednesday, don't forget, you will be doing your presentations on electrical design. Christian.
For the homework, did you ever change them like you said before the exam? Because I remember you mentioned that you were going to change the actual date on the homework because we're doing the exam. Okay.
The due date? Yeah, no, it's not, homework's not late. Yeah, I know that, I already said that.
Professor, you said we did another sim?
We'll do one more sim, yeah.
No, but previous to this one, we did another one?
Well, no, it was more of a homework assignment.
I didn't do that one. I didn't know.
Didn't we do one? No?
No?
Oh, then never mind.
Oh, okay. I was like,
Honestly,
what?
the years blur together. This is like the 8th year of doing this class and it's new 4. It just blurs together. So, no, okay, this is step 1.
Okay.
Okay, yeah, never mind.
I was like, oh my God, I missed that one.
What's that?
We did one for like an
That's what it was. Yeah, I was thinking for the competitive advantage. Yeah. Yeah, which 2 teams will get. I'm going to give you guys, when we come back from spring break, I want to have you guys demoing your electrical implementation. But my question to you guys is Wednesday, when we come back from spring break, too soon? Would you need another week to demo electrical?
Wait, I'm confused. So demo's separate from what we're doing this upcoming? We're
This
just
is a
presenting
presentation.
Oh, we're just like showing like.
This is the presentation mode. So you're presenting and making you guys demo. But we also have spring break in the middle. So my question is, do you guys, we can wait a week on the demo of the electrical. I'm okay with that. And I think you guys might need that extra week. But
What are you expecting on the demo?
basically, we need to drive the motors. It's very simple Hello World software. Your mechanical design is done. Your electrical design, so you may not have the motors mounted necessarily, but you can drive the motors, you can read the sensors. That the mechanical stuff is basically dialed in, and your electrical stuff is there. Your processors are working. Processors may not communicate necessarily to each other, but you have the basics of what needs to be done. So we can focus on the software afterwards. I'm thinking originally I was thinking doing the Wednesday when we come back, but it's okay if we do the Wednesday after that.
Can we wait that week then? Since we're losing a week during spring break to like use the labs and stuff.
That's why I was getting at. That's the point I was getting at. So you guys may not be able to work together easily, so that's why I was going to push it out. Let's just pull up the calendar here real quick, because we will get to the end of the semester really quick. So I'm talking about, we have spring break is on here, so I'm talking about, originally I was thinking of the 8th for the electrical design, or the electrical demo. So it could be the 15th of April instead. We can shoot for the 8th, and if you can't do the 8th, and you want it the 15th, I'll go with either of the two. Maybe you guys can do it on your own. So, no later than the 15th. Maybe if you say no later than, for sure if you want to demo your electrical design on the 8th, you can do that. But let's do no later than the 15th. Does that work for you guys?
Yeah.
Because before you know it, the 6th is going to be here.
And that's when we're done with everything, that's our compensating part.
Because finals is going to be, isn't it this week right here?
Yeah.
Yeah, which is why I was pushing. I really want to have the 8th as your electrical. So no later than the 15th, but let's shoot for the 8th.
Yeah.
Okay? Because isn't finals this week or is finals this week?
It's
It's the 11th, right? Okay, so we got a little bit of more time.
Isn't May the 8th our last day?
8th is the last day of classes.
Oh, the classes.
So the demo for you guys is the other question we have to talk about. We don't have to make the decision just yet, but we need to start thinking about this. The competition date, I've left it TBD. I've done it the week before, I've done it the week of finals. I'm good either way. I don't necessarily, we can do it on a Friday. We can do it on the 8th. Right before everything, come in, do it Friday morning in the lab, once the lab's available, I gotta make sure it is, the donuts and everything like that, yeah.
So our demo that we have for the class of fruit that we've like had the.
Proving grounds?
Yeah, that's separate from the actual competition.
You just have to do that, that's your bare minimum, but that'll be done with the day of the demo.
I'm still a little lost, I'm like, are those two separate dates or?
No, it's the same day, it's just you show, so everyone's there, okay, everyone's set up, yeah, okay, show me the proving grounds, I walk around and show me the proving grounds, we're good to go.
Okay.
And then because the proving grounds are gonna help seed you guys. The reports and the proving grounds will seed you. So I need the reports probably a few days before that so I can get some experts to review for seeding. I will grade them for grading, but not for seeding. I'll have,
Oh, that's the opposite of, because you did it for seating rather than grading in, TV, yeah.
it's the same thing.
Okay,
I'm grading the reports to grade them, but I'm not grading them to seed.
gotcha.
Experts will seed to seed you guys.
And then in terms of feedback from those experts, is that something that's happening like in person, or is that feedback that you're relaying?
Depends on when you guys get the reports to me. More often than not, you want more time just to do it than you want for the feedback time, so, yeah. We're good on dates, haven't you guys see what's coming up? Anything else? It's coming fast, isn't it?
Oh, yeah.
Anybody want something fun for spring break?
Let's say,
All week?
No, was it just basically planning for that, but I think near the end, I'm trying to get James to go, but his parents are kind of trying to trap him, so.
I don't blame you.
It's not.
Where's your parents? Where's your parents at?
Family the whole time, probably.
So I think they timed it so when he had back to figures,
For the electrical.
then I get him, so I can take turn fair.
That will be.
So I hope I'm just planning on catching up on them all. Oh, and I finished my mud run over
I need to remember the electrical network.
How did you do?
Only electrocuted just a few times.
It's mainly chapter.
I did it in jeans too, so I was covered from head to toe. It was great.
The two guys theory is bridging.
Yeah.
So we're going to continue our discussion on Jacobians. So the Jacobian, it's dealing with the differential aspects, right? So we're talking differential motion, but that's very infinitesimal amounts. And we're moving and we're mapping from one space into another space, much like we did with the transform. But now it's very different because we're not just dealing with the vectors, it's a velocity vector, or it's a vector of motion. And so we need to carry that around. And so what we'll have to do is we will be doing differentiation. But we're not going to differentiate like we did already. We're going to differentiate using partial differentiation. Some of you may or may not have done partial differentiation, but if you've done differentiation, partial differentiation is trivial. Right. Let me go ahead and just show what that looks like. Let me pull up the tablet here. I believe we are on slide. We just finished slide 11. I do plan to have Jacobians done. Will we get done with Jacobians before spring break? I don't know. I do have videos from Jacobians on from spring break because that's when COVID hit, and I did all of the videos on asynchronous. So those are posted on the YouTube site that you all have access to. So we are on lecture 5. How many are graduating? Oh, I gotta change that. No, that came out wrong, actually. The reason I say this is because autonomous vehicles is gonna fly in November, or not, in fall. So, I'm taking it. Come take it. If you're doing a graduate program, I think you can take the class then too. So I think Tom's doing it and a few others. So if you're gonna sign up for a master's degree program here, you can take the class as a one of your like a language or something. Okay, so we were on this area. She walked I don't know, she kind of walked in like she was barely walking, so. All right, so we were talking about, we did the last slide, yeah, so just kind of review what we were talking about, Jacobian. The Jacobian is going to map the components from one space to another space. But the components that we're talking about are velocities. So we're going to go from the joint velocities, the motors themselves. Because the motors, we don't control position, right? In motors, we control velocity. And so as we are controlling the joints of each one, we're looking and trying to describe this particular space of motion. When I say space, I'm speaking in the matrix sense or the vector sense, where I have these vectors that define a space. And so I've got the tip as it moves across like this. So in the simulation, you are going to the destination. We weren't necessarily caring about the motion of you getting there other than say, get to the end spot. Your second simulation is going to be managing that end space using inverse kinematics using Coppelius sim, much like I showed you guys on that inverse kinematic example of that robot when you move that dummy around. And so we have that end effector tip, that velocity, but it's controlled by the individual velocities that compose them. That's the velocities that we're talking about. So we need to convert the joint space to the end effector space and everything that goes with it. So to do that, we're talking about velocities, we're talking about these partial derivatives, we're talking about these differentiations. And so let's talk a little bit about this idea of a partial derivative. So a Jacobian is used all over the place. I mean, it is probably one of the most often used but least taught topics in engineering. I didn't actually have it when I was an undergrad. I took it in grad school. Here you guys are, we should have had it. My robotics class wasn't very good, I'll be honest with you. There's a lot of things that we left on the table. You guys get the advantage of me saying, man, why did we leave that on the table? Jacobians, we weren't talking about it, but we're going to talk about it here. So the Jacobian is really, it's a set of partial derivatives. And then these partial derivatives, they're applied in a function that has several variables with it. And so the idea here is that what is a partial derivative? And a partial derivative is the derivative is only taken with respect to one of those variables while the other variables are held constant. Now, at some level, this may make a lot of sense. What we're going to be doing with the Jacobian is we're looking for the contribution of each one of those joints, velocities, this joint, this joint, this joint, this joint, each one of those contributions of their own velocities to make this velocity. So we think velocity, we're thinking first derivative, aren't we, of a position. So we have theta dots, all these are theta dots. We want to know their individual contribution to this velocity. Now this velocity can be expressed for x dot, y dot, z dot, about x dot, about y dot, about z dot. So I can look at all 6 of those velocities. 3 are rotational and 3 are linear. 3 are angular and 3 are linear. But they all have components of each one of those joints' velocities. And so the partial derivative, what we're looking at, is a way of expressing the relationship of each one of those contributions of each joint to that x dot. Each one of those joints to y dot. Each one of those joints to x dot. What am I saying? Let's go back to what we talked about before. So here we are. The Jacobian is looking at each one of these positional dot variables, x dot, y dot, z dot, and the relationship for each one of these joints. So each one of these guys right here is going to have a contribution from any of these theta dots. That's described by that row. The next row is going to be the relationship for the next p variable, so y dot, for all of these guys. Make sense so far? Down here, same thing. So this third entry is going to be this third row. There's going to be all these contributions from each one of these angles. And so what we're going to be doing is looking at those contributions, deriving what those contributions are in totality. They're summed together. So there's some contribution for each one of these. The way we're going to do that is by taking the partial derivative with respect to only the variable of interest. So let's talk about partial derivatives before we go on. And so if we look at it, if we want to take, given some function f of x, y, z. So I've got 2x plus 3y plus 4z. And I want to take that partial derivative just with respect to x. treat everything else as constant. That's all we did. It's not partial different. This is not partial differential equations like PDEs. These are partial derivatives. They're a little different. Yeah.
What does it say after taking? In the red box?
With respects to WRT. So we're going to take this expression, so 2x plus 3y plus 4z, take the partial of that with respects to x. These are constants. Constants, the derivative of a constant is 0.
What's the term in front of that? Oh, for that fraction.
This right here?
Yeah.
That's the partial derivative.
Got it.
So we have the partial of f with respects to the partial of x. So that turns into 2. The partial with respects to y, that's a constant, that's constant. Just looking at that expression. Same thing here. We could also do it with higher order, not just simple constants. So in this case, if we're looking at this guy right here, take the derivative of this, we're going to get 6x. This y is a constant. It's just like another type of a 2. So that goes along as over a 2, but the derivative of x is obviously just going to be the 1. So here's the 2 is constant, the y is a constant, the derivative of x is 1, so we're going to get 2y. Same here, we can take the partial of z with respect to x. So again, z is this expression. And so here we take, in this case, we again have the same idea we had right here. The y, derivative of y is 1. The 2x goes along for the ride. Okay. That's what we have to partial. Oh, this should be
Why?
That should be a y. Thank
No.
you. I was looking at John's face going, that makes no sense.
No, I know.
I'm like, what doesn't make sense? Oh, you're right. So then we go along, and they said, obviously, we take that derivative, and that should actually be a minus. I gotta change my notes. Does that make sense? So that's partial derivatives. So it's the partial contribution of the velocities for each one. That allows us to go to the notion of Jacobian. And so what we're talking about here is we're going to go, let's just say in generalities, I'll say y equals fx, okay? So we're going to simply say a y, make them bolded, we can say something like this, is going to be the Jacobian matrix. We could even call it J, doesn't really matter. And this is my x. And so we can relate this, think of this as a set of terms. So f is a set of terms that we can write out. So we're going to take our f1 term with just our x1. For each one of them, for each one of those j terms that we have right here, where we have x1 to xj. This is the y1 all the way down to yi. So we have f1 x1 to xj, f2 x1 to xj, all the way down to I of these relationships of f to x. So we're going to have fi x1, fi xj. So the y equals fx. We could consider those to be the velocities of b in the x direction, or the x component, and the y component. That's what we're seeing right here. So we have the x component and the y component. So f is describing that relationship. So given x, I've got a y. And that y can have, it could be the velocity. This is, you can consider this to be a vector or a matrix, and we can look at it like that as well. So we have the individual components right here of yi. So each one of those i's of y has a function. And that function can have up to j expressions. Doesn't need to have all j, it could have half of the j's. It doesn't matter, but we can have no more than j's. If we have more than j's, then we run into problems of being overdetermined. And that gives us bigger problems. We're not going to worry about those bigger problems. Then we get into graduate classes and singular value decompositions and rank reductions through DMDs and things like that. So here we are, there's I rows and Y. So that means there will be I functions of X in F, but there are J X elements. Again, think of this right here. This is the number of motors, i.e. 1 for each joint. This right here is going to be the velocities, say Vx, Vy, Vz, and we can say V about X, let's call it alpha, beta, gamma, or psi. Does that make sense? So about X, Y, Z and along X, Y, Z. And so there's some relationships that we can map from these joints here to the tip velocity there. As it maybe it rotates like this, or moves. Or maybe it's doing this. Yeah.
So you wrote the 3 velocities and then the 3 rotational velocities?
Yep. Oh. Yeah, so it could be whatever we want. We could say, we can decompose it, so this would be my linear, and this could be my angular. It doesn't matter. That's what we're describing in our realization. The Jacobian doesn't care. The Jacobian simply says, I've got this differential relationship. You guys may not have had the gradient yet, but it's a lot like the gradient that we're talking about, where we're taking the derivative of each one with respect to the other, defining that surface. But not everybody's had gradients. Yeah.
So the Jacobian kind of isolates which I don't want to say frames.
No, it's the contribution of each of this differential amount. So there's some differential amount of motion. Some differential amount of motion of theta dot. Theta dot 1, theta dot 2, theta dot 3. Right. So we have a 6 degree of freedom robot. Each one of those has theta dots. So a theta dot 1, theta dot 2, theta dot 3. For each one of the joints, there's a velocity.
Right.
Which is what we command. We don't command a position of a robot. We command the velocity of the motor. Commanding the velocity of the motor, we need to make this motion of this end effector what we want.
And then when we get the angular, the alpha, beta, gamma, is that a different matrix?
No, we just have to relate what those velocities do. And we'll get to that point. We're not there yet. So we have some space to another space, related through the Jacobian.
So then, when we're talking about, because we talked about relative motion earlier, since functions are.
Yes, we'll get to relative motions. That's going to be at the very end. Yeah. Okay, everyone good on this so far?
Yeah.
All right, so 15. So the Jacobian matrix, let's put a little bit more truth to this. So we can say that some function exists, yi, which we can write as f of x1, x2, up to all the x's that we have in our joint space, for example. We want to find the differential relationships for each yi to each of all the x's. Let me say that. So we want to find the differential relationship for each yi. So there's I number of these y expressions. Find the relationship of for each yi to each of and this is bad English, to each of all of the x's. What is x1's contribution to y1? What is x2's contribution to y1? What is x3's contribution to y1? We're talking about the contributions of the differential motion. So that's where we use the partial derivative. So what we say is we're going to say that y differential I1 is going to be the partial derivative of f with respect to the partial derivative x1. And then we're just use this notional term right here, x1, partial f. I'm sorry, dx1. Plus, we do this for all possibilities. So f one right here. We need a one right here.
What about next?
Yeah, I need an x too. This is where it becomes an accounting game of what I wrote and didn't write. All right, so partial first row of f on the jth x with respect to the jth x for j xj. And we have, I don't know how I wrote so small on my notes and not have enough space when I do it, but we'll get through. Partial y2 is going to be f2 with respect to x1, f2. So now we'll get all the f2 functions, all the second function relationships, right? Then we do the third function relationships, and so on and so on. This is respects to x2. All the way down to the ith expression of y, which is the function that relates these two things together. So the ith function with respects to our first x. For each one. Now, that's a messy way to write it. We can be much more sacient when we write this using some vector or some matrices, some linear algebra. So we can come through and say we're going to simply say y1, y2, yi. You get the Jacobian. And then we have x1, x2, x2. So we have inside here the elemental terms. So we're going to have the partial derivative of f with respects to x1, the partial derivative f1 with respects to x2, partial f1 x3, partial f1 with respects to xj. All the way down to partial fi. So I'll try to write below that black line so we can see a little bit better. The first element, partial fi to x2, all the way across fi partial f xj. And so what we see right here is this guy right here is, we can call this the D matrix, or the differential of the tip. Niku likes to call that the D vector, the D matrix. This right here is our Jacobian. And this right here is going to be our differential motion of our thetas. So this part right here is our differential motion of our end effector of this space as it moves across. This is the relationship in the contributions for each one of these guys over here. And so we're looking at the individual contributions. These are the elements of motion, these are the differential motions, and this is what relates them all together through the partial derivatives.
Does the vertical order matter? Like we have to start from
Yes.
one?
Yes. Yeah, because this will go, again, this times this plus this times this plus this times this. That's exactly what we have right here. Right? So if we do the matrix multiplications, we'll formulate what we have up on top. Question?
So all of these are, all these dy, dz, d, all that, is that just point us like in the general direction of where we want to go?
Yeah, so this actually is very specific. This tells us, so this right here could be my x dot, my y dot, my z dot, about x, about y, about z. Right now, this is still in very general form, right? But this is what's going on right here.
Is that what you say? It's like the gradient in a way?
Yes.
Okay, that makes sense.
Okay, clear as mud so far?
Yeah.
Does everybody have that slide? Are we good? It is in the book, by the way. Are we good? Go on. So, what we're saying is that we have our partial of our y's, or our differential positions, is equal to each one of those functions so J is going to run from 1 to the number of x terms, and I is 1 to the number of y terms. So we could think of this as Cartesian space. It could be any space, to be quite honest with you. We could do this in polar space. We could do this in spherical arm space. It doesn't really matter. But we're going to talk about this tip, which happens to have x, y, z, about x, about y, and about z. Because that's what we're talking about for a robot tip. In a more general sense, it doesn't matter. So that is going to be the Cartesian space. This is our Jacobian. And this is going to be our joint space. And so we're left with this idea where we have D equals our Jacobian times our joint space. Or the way Niku likes to write this is D is defined as a dx, dy, dz, delta x, delta y, delta z, so a little delta. So this is the translational. And this becomes the rotational. So this is the rotational velocity about x, the rotational velocity about y, the rotational velocity about z. Dx is a rotational velocity along x, along y, along z, for the end effector. So this is the end effector. equals our Jacobian, J, d theta 1, d theta 2, d theta 3, d theta 4, d theta 5. We're not going to go past d theta 6. That's what we have. So you will be doing 6 by 6 multiplications. Your exam, you may be able to use MATLAB. Yay! It's a take-home exam. You're in class is essentially your oral presentation, which is your oral examination.
How worse are your take home compared to class?
They're easier.
They are much harder.
You got like a week to do them.
That's not a good thing.
I know it's not.
It gives you time to reflect.
Or question your life.
All right, so the Jacobian is taking the individual contributions for each one of these joint velocities and relating them to the end effector velocities right here. So this is end effector velocities. And these are the joint velocities. That's all the Jacobian is. So when we watch the example of the inverse kinematics robot, see we have I'm wondering, now that we've seen this, if it's more appropriate, you guys want to go back to the simulation of the inverse kinematics where we can see the Jacobians actually working?
Yeah.
Now that we have an idea of what we're trying to do, right? So now we begin to go, oh, we talked about this inverse kinematic method and how we use the Jacobian. That makes sense because I can, from the Jacobian, if I know my velocities, I can figure out my thetas, can't I? If I know my Jacobian. If I can figure out my velocities, I can integrate those and get my positions. So I can get my position 1 to my position 2, can't I? So my inverse kinematics through the Jacobian becomes more realistic. So we talked about those algorithms. I said, it's the Jacobian. It's the Jacobian. We'll talk about it later. Well, now we're talking about, now you begin to see how that Jacobian is relating joint space to end effector space. End effector space, inverse kinematics. Now we go from here to here, right? Using the Jacobian, I can do that, but I have to integrate these velocities. But like, okay, it's not a big deal, right? Okay, let's go back now, and let's look at inverse kinematics again. And I need this one. I'll be honest with you, I don't know how many professors who teach robotics go into this much detail. Good, bad, or others for you guys.
Do other professors even use Copalia for robotics?
No.
Do you know what route they take?
No. Aside from the there it is, 5K. Okay, so let's turn on visualize IK worlds. Okay, so here is our Jacobian. Oh, 1, 2, 3, 4, 5. How many joints do I have?
6.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 is my space. X, Y, Z, dx, dy, dz. Delta x, delta y, dx, dy, dz. That's a 1. All right. As this moves, I'm going to move the ball. There's my Jacobian. What's wrong one? Hang on a second. I'll grab the wrong one. I want the destination tip. not the source there. So each one of those, let's go ahead and move along, X and Z, so I can get some arc in there. Each one of those, at any point in time, is being calculated as that ball moves. We can write expressions, mathematical expressions, and we will do that next. But at any point in time, any one of these guys down here is at a particular velocity. And that's why they're always moving. But when I'm stopped, theoretically they should all stop, unless it's kind of wiggling because of simulation or some numerical stability. That's why we use them in IK, as I'm doing right here. As it's trying to figure out how to get that robot there on the fly. The Jacobian is relating the joint velocities to that end effector, which is actually defined as this tip right here, current tip. Destination tip is where it's going to try to follow, if it can. If it can't, it'll do its best. But this is the Jacobian. I still haven't figured out what the different colors are for. That's why I haven't looked into it either. I wonder what the colors are for. Oh well. Something else to worry about. I'll probably look it up now that I'm thinking about it. Huh?
Extra credit.
Extra credit if you can figure out what the colors mean.
Some sort of white, it's more white.
That's what I'm thinking. White's.
White
Right, it's
zero.
closer to 0, yeah.
Yeah.
Oh, yeah.
Do we get extra credit?
Sure.
Yay.
Yay!
I don't know how to give you extra credit.
Yes.
I'll just give you credit.
Yeah.
Well, there's the credit. All right.
Do we get a name?
Sure. I'll give you an attaboy.
Okay.
Does this make sense? Does seeing the simulation kind of put the two things together?
Yeah.
Now, it turns out, can we use our transform relationships, our forward kinematics, our DH parameters, our T's, to develop our Jacobians?
Yeah.
Absolutely. And that's what we talk about next. Everyone so far so good? Read the book, please. I kid you not. Read the book, read the book, read the book. But the book will make more sense now, I promise. We can do the next slides a couple of different ways. There's only a handful of slides. I don't write on any of them. Well, I guess I do. But we can just stay on here. Is that okay? We just stay on here? So you'll see what I have written instead of me writing it. So the Jacobian. If the functions for F1 to Fi are nonlinear, we linearize them. We generally will linearize them strictly to the first term and consider the high order terms to be noise that we can ignore. So if the derivative for x1, that is, for example, dx dt, then the Jacobian is going to map that dx dt to the dy dt values. That's really what we're doing here. So if we look at the items x in its own space, J is mapping x into the y space. In other words, joint space, Cartesian space, or end effector space. Niku uses those two interchangeably. So for every time as x changes, the calculation is being performed. Now there are expressions that we'll get to, I think on Wednesday, where we actually arrive at the expressions of sines and cosines. But we did that already. Where did we do that? Right here. This is my Jacobian. At any point in time, I'm calculating dx and dy for my values of theta 1 and theta 2 as they relate this guy right there. And we did that by differentiating these equations, didn't we? That's how we got to this point. And then we kind of made them look pretty. As it moves, as theta moved on that robot arm, so too did these values change. So there really is no magic what's going on. Y'all believe me yet? Wade's like, no. Speaking of words, Will, not here. See what happens when I know your name? And thank you, Robert, for being here on time.
I was actually voting 4 minutes late.
Why you gotta run?
Just take it. Maybe not 4 minutes late and then, I don't know. But, so this is what we've got going on here, right? So we derive this, we can drive these for all of them. Like we can do the manual version. But we really also know that these relationships are very similar to how we did the transforms, right? This is how we got the rotation matrices, our T's. In fact, when we did quaternions, we saw a really simple way to do that, right? Okay. So, we're continually, as it's being rotated or moved, at some delta t, computing the value, some differential amount of time, some very, very small, infinitesimal small amount of time. Now, in calculus, if this is a smooth function, and realistically it is, why can I say, why do I say it's smooth? Let's go back to that. Why do I say that this is, in fact, a smooth function? You want to venture a guess on it?
Continuous.
It's continuous. Well, it's continuous to a point. I'm going to hold that thought and come back to it. But this guy, this end effector, does not automatically, I mean, it has to follow laws of motion. It does not do teleportation. It doesn't go here and then magically show up right here. I mean, I guess it looks like it's definitely don't say this. Go back to destination 2. Right? So it doesn't transport. It has to follow some smooth motion profile. Right? So yes, it is smooth. I mean, yeah, you can make this look kind of jerky, but it's following smooth motion. But I have to sample it at certain delta t's, some very small t's, but they're delta t's nonetheless. In calculus, we took the limit as delta t goes to 0, right? That's how we got perfectly smooth motion. But we don't do that in the real world. The real world has to live in delta t's because we're continually sampling. For that lecture, I would say take DSP with me in every other fall, and we'll go through that in gory detail of sampling theory. But right now, just know that we're not doing it continuously as delta t is 0, but there is some infinitesimal delta t, some small delta, like little delta t, for the big delta t's. We're going to be moving every single so far along. At those delta t's, we're doing that calculation in the 2-joint arm. Actually, what I probably should do is do that planar arm right here and actually show the sine cosine. That'd be a good extra credit assignment. That would be a really good extra credit assignment, wouldn't it? Build a planar arm, show the Jacobian relationships per the equation that we derived. Oops, wrong class. This one here. For this matrix right here, just 2 joints. Now, your exam is going to have 3. I'll tell you straight up, your final is going to use a 3-planar arm, and you're going to have to find the Jacobian for it. I'm going to tell you what your final's got right now on it. It's not that hard. Okay? You can start thinking about how to do that. I might even give you guys an assignment, maybe for Sim 2, to do that, so you get a jump start on your final. I don't know. Let me think about that one. But it would maybe make the Sim 2 more meaningful. So you have to do the analytical exam when you've got the hard copy that's already solution size in Coppelia. And again, here's your Jacobians right here. This is going to be in probably in radians would be my guess for units. But they're just values. These are just values of relationships. But that would be a really good assignment to do. There's an extra credit to a 2-planar. Y'all want to do that? You want that as an extra credit assignment? You don't have to do it. Maybe we should do it as, oh, hang on, wait a minute. It's getting worse. No. Competitive advantage 2.
Yeah, sorry.
Competitive advantage 2 is a Jacobian of your arm. That matrix, and how does that fit? Do you guys have, I think you guys could all, but you guys don't have to do the Jacobian just yet, right? We have not talked about how to do DH parameters to Jacobian. So we won't have, I'm not going to make you guys do the derivation from this. There are other ways to do the Jacobian. We'll talk about that. So let's talk about that next. Here we go.
Quick question.
Yes, sir.
For the extra credit that was just mentioned, do you have an idea of what our competitive advantage would be?
Yes, your competitive advantage is going to be probably more build time or more build blocks.
Okay.
So it's more build blocks, doesn't mean the other team has more.
More build blocks means you get more points.
Wait, but doesn't that also mean the opponent gets more points if they destroy more blocks?
Depends on how you stack them. There are ways you can think about this that you're not even thinking about yet.
That, I'm aware. I don't want to think about that yet. It's just getting the damn thing built.
So, competitive advantage for, you already had the offense competitive advantage. For the defensive competitive advantage, Jacobian of your arm. But you know what? Let's go one step further. You do the inverse kinematics of your arm with Jacobian, you get one of them. You choose one or the other. Time or blocks. You do both of them. In other words, you do the Jacobian matrix of your arm, not just the simulation with the Jacobian I just showed you guys, but also do come up with what that matrix looks like or how you derive that. Analytically, you get you get two competitive advantages for construction. Does that sound good? There's some truth in that one. We'll talk on Wednesday. So let me mull it over, but that's my thoughts. You guys mull it over too. Okay, I'm running out of time real quick. Okay, so let's just look at the slides here real quick. So in Jacobians, we know the robotics, the velocities, the manipulator, depending on the joints. Okay, we talked about everything I've talked about. This is kind of summarized because everything I said. The dependency, they're going to be based on the transforms from one joint to the next. We're going to see that coming up. The Jacobians providing the relationships, the joint velocities between the base frame and the tip frame. And that's why the transform T's come into play. Because that's how we pick up all the joints, J1 through J6. Why do we care? Because we can only control the joint velocities. We can only control motor velocities because we can only give the voltage it wants at the current it demands. The tip velocity is 2 or more additional joints. So, how do we get there? So, in Jacobian space, really what we're talking about here is just from transforms. So, we have to figure out how we're going to go from transforms, T's, to J's. And that's what we're going to go through. We won't finish today, I already know that. But so I want to start looking at that. So, the idea here is that the number of columns is going to be equal to the number of joints. That's this guy right here in the Jacobian, which is the same as the number of rows in that theta space, right? The joint vector has the number of rows as the number of joints. Which is what I just said. And so we see right here that we've got this L, here's a theta, here's frame 1, here's frame 2, here's frame 3. So our frame 0 is 0. So we have a transform from 0 to 1, from UCF to joint 1, and that's this guy right here. And then from joint 1 to joint 2 is this guy right here. And then our tip right here is our end effector. So we can create, we already know how to do this now. This is on the exam. This is what we spent all chapter 2 studying, was how to derive T0 to 3. In T2 to 3 is nothing more than that length. Everything else is identity. Because there's no joint, it's just an offset along that X direction. So now we want to figure out how we develop J given T. To do that, we look at bar rotation. With that being said, I'm going to go ahead and call it here. I want you to start looking at these slides, but we're going to find out how R relates to this thing called S. And then from S, we get the velocities, and we get what's known as our S matrix. Okay. We'll pick it up.